In this mini lecture, we're going to see how to get from part 1 of the fundamental theorem of calculus to part 2 of the fundamental theorem of calculus, the really practical one that tells us here's how you evaluate integrals. Okay, so I suppose it makes sense to start with the statement of part 1 of the fundamental theorem of calculus. And that statement tells us that if we start out with a continuous function f on an interval a, b, we build up the area function g of x given by the integral from t equals a to t equals x of f of t dt. It tells us that that function is continuous, it's differentiable, and really importantly, its derivative is equal to little f. So when we calculate the area under a function between t equals a and t equals x and ask the question, how quickly is the area changing as we move x? The answer is equal to little f. Okay. But how does that help us to calculate this integral? And these are the practical problems that we'll have to deal with. Okay, we'll have, often coming from applications, we'll have a need to evaluate an integral like this. We'll have a function f of t, we'll have values for a and b, and we'll want to know, well, what actually is this number? How do we calculate it? Well, the answer to that, as we know, comes from part 2 of the fundamental theorem, which tells us that the way we do this is to calculate an antiderivative. So we undifferentiate the function little f to find this function capital F. Any function with the property that capital F has derivative equal to little f. We evaluate that function at t equals b, at t equals a, and subtract, and there's our answer. Okay, so these two things seem to be saying quite different things. So they are linked. The first part of the fundamental theorem and the second part of the fundamental theorem, they're linked by the fact that they both involve areas and integrals, and they both involve derivatives. So let's make that connection now. Okay, so to understand how the second part of the fundamental theorem works, or let's say rather, why is it true? Let's take capital F to be any antiderivative of little f on the interval ab. So capital F is going to be any function whose derivative is equal to little f for all x in the interval between a and b. Now, from part 1 of the fundamental theorem, so when I say part 1 there, I mean part 1 of the fundamental theorem of calculus. From that theorem, we know that the area function also has this property that its derivative is equal to little f for all x between a and b. Okay, so we have on the one hand that any antiderivative, by definition, any antiderivative of little f satisfies capital F prime equals little f, whereas this area function g also satisfies the same equation. Its derivative g is equal to little f. So if I look at the derivative of the difference little g minus capital F, what will that equal? Well, the derivative of g is g prime, the derivative of capital F is capital F prime, and from the equations in red, well, we know that g prime is equal to little f, and we also know that f prime is equal to, capital F prime is equal to little f. So the result is 0. Okay. So just get rid of those slightly distracting arrows. What do I see there? I see that the derivative of this thing here, little g minus capital F, is equal to 0. Now, I know about functions that have that property. What kind of functions can we differentiate, which will always give 0 as the answer? Well, there's, in some sense, only one possibility. This can only happen if little g minus capital F is equal to a constant number. Okay? So the only thing that we can differentiate and get 0 is a constant. So if I have some function, let's say k of x, what I'm using here is the fact that if k prime of x is equal to 0, let's say if it's identically equal to 0, so it's equal to 0 for all x's, then k is constant. K must be just a constant number. Okay, so let's exploit that fact. So we now know that if I start with any antiderivative capital F of little f, if I compare it with the area function, well, their difference must be equal to a constant number. Where does that bring me? Well, I can make this statement, which is essentially what I just spoke there. Given any antiderivative capital F of little f, it tells us that there's some number, some constant number k, such that g minus capital F is equal to this constant number k for all x's in the interval. Okay. So this, no matter what value of x I choose, I always get the same number k. Okay, that's what it means to have a constant function. We always get the same output, if you like. So g of x minus f of x is always equal to the same number k for all x's in the interval. And there's two x values of particular interest there. There's the values at the endpoints. So for example, when x equals a, well, this number k equals g of x minus f of x, but it's always the same number, regardless of the value of x. So when x equals a, this equation tells me that the number k on the right is equal to g of a minus f of a. Why is that? Because no matter what value of x I use, I always get k. Likewise, sorry, before I say any more, let's just look carefully at that number. What's g of a? Well, g of a is the area function starting at a and ending at a. Okay, so what have we got there? We have a zero area. Okay, we haven't moved away from a. Okay, so the area under the graph of little f between t equals a and t equals a, well, that's zero. We're actually looking at a line segment which has zero area. Okay, so I can evaluate there and I find that the number I get is zero. Okay, so that, if I look at that carefully, actually, that tells me I can extract from there actually the value of this number k. It must be equal to minus capital F of a. Okay, so that's a useful finding. At x equals b, on the other hand, what does this equation tell us? It tells us that, working from the right, that k is equal to g of b minus f of b. G of b, well, g is the area function, so g of b is the total area under the graph of f between t equals a and t equals b. Okay, so that's g of b. That's straight from the definition of g. And then I'd be subtracting f of b. But let's remember, from the first equation here, it disappeared when I moved on. From the first equation here, we found that k is equal to minus f of a. Minus, sorry, I need to be very careful there, minus capital F of a. Let me delete that actually. So that equation there gave us the result that k is equal to minus capital F. So in this equation here, I can substitute that number. K is equal to minus F of a. And now, if I ignore the bit in the middle there, minus f of a is equal to the definite integral minus f of b. And just a little bit of rearranging there gives the desired result that the integral from a to b of little f of t dt is capital F of b minus capital F of a. Because remember, k there on the left was equal to minus capital F of a. Okay, so there's a little bit of maneuvering around here, but we see that this part 2 of the fundamental theorem comes straight from part 1 of the fundamental theorem. Okay, we get the integral from a to b of f of t dt is capital F of b minus capital F of a, where capital F is any antiderivative of the original function little f. So there's our fundamental theorem of calculus, as I've just stated it. If f is any continuous function on the closed interval from a to b, then the definite integral from a to b of f of x dx is capital F of b minus capital F of a, where f is any antiderivative, that is any function with the property that capital F prime is equal to little f. Okay, so that's how, that's really the key result that we use to evaluate integrals. For the next sequence of lectures, beginning with the next one in this sequence, we're going to look at how to use this theorem.